And I'm glad to introduce our next speaker. It is Dr. Gianni Pagnini from Basque Center for Applied Mathematics. And the topic is, should I stay or should I go? Zero-size jumps in random walks for Lévy flights. Please.
I don't know if you're still muted, so let's see if you can unmute yourself.
Sorry.
Okay, now it's fine. Thank you very much.
Okay, so maybe even the camera is not working, but okay, doesn't matter. So thank you very much for this invitation, and I was saying that it's very emotional to see this workshop. So maybe for me it's good to stay at home because to be there it will be very emotional. My name is Gianni Pagnini. This work is in collaboration with the previous postdoc in my research line, Silvia Vitali, and the paper has been already published. It is in open access, and the reference is below the title. And the research concern a doubt that I have looked into this continuous time random walk for Lévy flights, and this concerns the fact that when we have a Brownian motion, actually we don't care if the jump distribution is unimodal, so it is Gaussian or something like this, which it means that in the majority of the iteration, the particle doesn't move, or if it is bi-modal, which is 0 in 0, which it means that the particle always moves. And when we have the Brownian motion, this is not an issue, because we know that if the jumps are Gaussian or if the jumps are according to two delta functions, after a while we recover the Gaussian PDF for the walkers. And so the research was based on this doubt: what happens when we have unimodal or bi-modal jump distribution for Lévy flights. Actually, I was not able to find something about this in the literature, and so this was the topic of the research. Okay, the research is funded by both at the regional and the national level. Then the meaning of the title comes from this idea that when it is a unimodal, then the particle remains where it is for the majority of the iteration. So should I stay? And in the other case, when the distribution of the jump size is bi-modal and it is 0 in 0, which it means that the particle always moves. And then this is should I go? Okay, so if we want to derive Brownian motion, one of the standard procedure is this given in integral 1. Rho is the density function of the walkers, phi is the distribution of the jumps, delta x is the jump length, and then we have this iteration through integral 1. We can obtain the distribution of the walkers at time t plus delta t after a jump delta x. And so we can perform the Taylor expansion on both sides. We can use some symmetry, and at the end of the story, we arrive to the diffusion equation given in 2. And here we can see that the diffusion coefficient is given by the variance of the jumps. Okay, up to here, everything is very well known. And then the point is, but okay, what happens if the supremum of my jump length is in 0, and what happens when the infimum of my jump length distribution is in 0 and it is equal to 0 in the case when the variance of the jumps goes to infinite. And so we cannot apply the previous procedure because we don't have the diffusion coefficient with the same definition. And there is this very nice paper by Enrico Valdinoci where he derived the fractional diffusion equation by setting in a lattice the integral equation 1, And he introduced the power law for the jump length, and he introduced even this condition that the jump length the PDF of the jump length must be 0 in 0. So it is a bi-modal jump distribution. And and then we have also some convergence condition. And at the end, he derived the fractional diffusion equation with parameter alpha that ranges between 0 and 2. And what is nice that if you look to the fractional Laplacian, the singularity of the fractional Laplacian corresponds in some sense to the bimodality that Valdinocci put in his derivation. But this is not the way that the fractional diffusion equation is derived in statistical physics. In statistical physics, the procedure is more close to the one for the Brownian motion. So you have this integral equation. You can recognize that it is a convolution in the Fourier space. So you start to introduce the characteristic functions. And then about the jump distribution, you can introduce the small wave numbers approximation. And so if you have this power law k to the power alpha and the small wave number approximation of the characteristic function of the jumps, then you have the fractional diffusion equation. And a slightly more general derivation of the same you have when you consider the continuous time random walk. The Walker distribution in the Fourier and Laplace space is given by the Montrol-Weiss equation. We want to stay in the much more simple setting, so the waiting time distribution is exponential, and I introduced this time scale tau, which is the mean waiting times, and then you have that actually the characteristic function of the Walker distribution is given in 4, and again, when you apply this small wave number approximation for the distribution of the jump length, if you have the power law, then you have the fractional diffusion equation. So through this procedure based on the small wave number approximation, you do not care if the jump distribution is unimodal or bimodal. And then let's see if there are some special cases where we can observe actually differences between the two distribution of jumps. So if we are in the Brownian case of the Brownian motion, alpha is equal to 2, no matter, we know everything. So if we are in this should I stay situation, so the distribution is unimodal, we can fix the jump size according to a Gaussian. We can perform small wave number approximation. And then we have this alternating series and we recover standard diffusion. If you do the same with the 2 delta function with the Galton board given in 6, and then again you have the characteristic function of the jumps, small wave number approximation. Again, you have an alternating series, 1 minus plus minus plus. And what happens is that actually the two processes are coincide, or they converge to the same Gaussian distribution. These are the plots. On the left, we have the two different characteristics, the two different jump distribution. One is unimodal, the Gaussian, the other one is the paradigmatic case for a bimodal jump distribution. But after a while, there is no differences in the distribution of the Walker. Okay, now we want to repeat the same in the case of a jump distribution with power law tails in order to recover, instead of Gaussian distribution, to recover Lévy flight and the Lévy distribution for the Walkers. And so if you want to have the analogous of the Gaussian jumps, then we are in the should stay condition. So the distribution of the jumps is unimodal, which it means that the majority of iteration the particle doesn't move. We set directly a stable distribution. We can compute the characteristic function, and everything works because, again, this small wave numbers approximations of the characteristic function of the jumps in the unimodal case is an alternating series. And then we can recover through the Montrol-Weiss equation the fractional diffusion equation. Okay, what happens if we introduce the generalization of the Galton board of the 2 delta functions when we want to have a bimodal distribution of the jumps, power law tails, and equal to 0 in 0. So actually, I'm trying to introduce the idea of Baldinoci into the continuous time random walk setting. So the first case, 8a, is given by this extremal Lévy densities, which is a probability density function on the semi-axis. So we have two of them, and then we divide it by two, one in the positive axis, the other one in the negative axis. And when this alpha goes to 1, we can recover the two delta functions. And but in this case, alpha ranges between 0 and 1, and so the stability index of this example ranges between 0 and 1 as well. Indeed, in the other example, 8b, just with the trick to introducing 1 over x, we have that indeed the stability index ranges between 1 and 2. So the two cases was just to introduce the full range of the stability index. And then when alpha goes to 1, we recover the delta function, and it is not, however, included in the problem. So alpha is equal to 1 is not included in this modeling. So what happens now if we want to proceed as is known from statistical physics? So now we pass to the characteristic function of the jump distribution. We perform the small wave number approximation, and now we have these two trigonometric functions. This function could change sign. So when alpha is ranging between 0 and 1/2, no problem, it remains an alternating series. But when alpha is between 1/2 and 1, we have that indeed this nice small wave number approximation of the characteristic function of the jumps is no more an alternating series. And so the solution, the convergence of this process actually is no more the single order fractional differential equation, but indeed is a double order fractional differential equation. And then in this narrow case, alpha between 1/2 and 1, however, the solution is not a Lévy density, but it is the convolution between two Lévy densities. Okay, no problem. If we look to the tails, we can recover what we know. But what happens is that indeed in the bulk of the distribution of the Walker, we have lost the self-similarity. While indeed, okay, sorry, and these are the plots. So when alpha is less than 1/2, no problem, both in the bulk and in the tails, we have that everything works. But indeed, when alpha is larger than 1/2, we can recover self-similarity, we can recover scaling, but for the tails, indeed, in the bulk, self-similarity is lost. This could be a second order effect for sure, for diffusion, no matter, but indeed, it is important when we look transiency and recurrency of the process. And indeed, in the other case, 8b, no problem. We can develop the small wave number approximation. We have again the trigonometric function, but there is no changes in the sign. So actually, this is an example quite straightforward as a generalization of the Brownian motion. And inside this example, we have this interval for parameter alpha between 1/2 and 1, where indeed the convergence to the Lévy flight is not so fast as in the other case. And then this is another paper by Baldinoci, co-authored by Serena Di Piero and Elena Fili. And here they derive this observable capital Q, which depends on the scaling in time of the bulk of the solution of the fractional diffusion equation. This BR is just the ball around the maximum, but the maximum is located in 0 in this diffusion problem. And so what about recurrency and transiency of the problem? So if we have stable density, and then we are in one-dimensional case, when alpha is between 0 and 1, the process is transient. So it is actually, in principle, the situation where we are. And indeed, when alpha is between 1 and 2, the problem is recurrent. When indeed the dimension is larger or equal to 2, it is always transient. So if we are in a one-dimensional case, let's see if this bi-modality introduces some effect, and actually it is. So If we look to very large time, no problem. The decreasing in time of the maximum of the Walker distribution goes like we expect. But this very large time given in 17 depends on a time scale, capital T, which is given in 18. So actually, the large time limit is observed after a very large intermediate regime, because when alpha goes to 1, we have that this capital T goes to infinite. So the point is that actually, when we have this continuous time random walk with a bi-modal probability density function for the jumps that is equal to 0 in 0, the risk is that when we observe the result, we are actually looking not to the asymptotic limit, but in the intermediate regime. And then what is the behavior of the maximum during this intermediate regime? Actually, 19 is not calculated. It is estimated by the plots. We were not able to give this formula. This is just the nice formula for fitting the simulation. And these are the simulations. So we can see that this is the decreasing in time of the maximum of the Walker distribution, and the decreasing in time goes through the expected power law, but for a large time. And indeed, when alpha increasing, we have this intermediate regime where the decreasing in time actually is not the same that we have for very, very large time, and the duration of this intermediate regime is longer as alpha grows. And how it behaves, so this plot comes from the simulation. So we have that actually when alpha is between 0.6 and 0.9, for example, so we stay away from the boundaries, we have that the duration of the intermediate regime is 2 orders of magnitude longer. 0.6, we are more or less 1, and 0.9, we are more or less 100. So actually, the intermediate regime could be very, very, very longer with respect to the mean waiting time. And actually, what we observe that when longer is this intermediate regime, higher is the decreasing in time. And so it happens that our process with alpha less than 1 has a decreasing in time in the maximum with a power law that indeed is higher than 1. And so the process in principle is transient, but we have this very long intermediate regime where the decreasing in time of the maximum goes with a law that suggests for a recurrent behavior. Then I'm going to provide the conclusion. So actually, at the end of the story, maybe looking to the unimodality or the bi-modality of the jump distribution could be important, maybe not for diffusion, but for other properties of the process. In particular, if we follow the approach by Valdinoci, it is possible to recognize the singularity of the fractional Laplacian with the value in 0 of the bi-modal distribution of the jumps. This effect is totally lost when we consider the small wave number approximation. So we do not have any effect from the specific shape of the jump distribution. But one of these effects would be related to the loss of the self-similarity, which is not a problem for large time and for the tails. But it introduces this intermediate regime that could be very, very long. And during this intermediate regime that could be very, very long, if we consider this for real processes, as an observation for real processes, we can find that decreasing corresponds to a recurrent process, while indeed the process is a transient one. So whenever we want to apply these processes, then since speaking about recurrency, it could be connected to searching for food or searching for home. So we can have that indeed, when we want to apply these processes to real phenomena, maybe we have to take care if the jump is unimodal, so in the majority of iteration, the walker doesn't move, or if it is bi-modal, which means that in majority of in always the iteration, the particle moves. And so, and I have finished. This is the reference of the paper. Now I try to put the camera. I don't know how to put the camera.
Thank you very much
Okay.
for your nice talk.
Okay.
Okay, we can see you now. Do you have some questions or comments to this talk? Okay, can you tell me, please, what kind of fractional Laplacian regularization did you consider here?
No one specifically, because this is a free boundary problem.
Okay.
So all the definition of fractional Laplacian works.
Okay, just regular, yes, standard. Okay, do you have much more questions?
Consider diffusion processes. I have in mind Brownian motion, so anything for me is a modification of Brownian motion. So I think that the spectral one is the best one.
Okay, I see. If we do not have any more questions, let's thank the speaker again.
Thank you very much to you.
Thank you very much.